Hi, I'm Felix Herrmann. I will present the lecture A New Take on Full-Wave Inversion, Wavefield-Reconstruction Inversion. Okay, so this is roughly the outline of my talk. I will start with a brief motivation, and then I will extensively talk about how you can compare the sort of conventional used adjoint state full waveform inversion technology versus this Wavefield reconstruction inversion, the topic of this talk. And I will end by comparing the performance of FWI on examples where FWI is known to fail and show what the benefits really are of Wavefield reconstruction inversion for velocity models that have low velocity kickbacks or high contrast, high velocity unconformities such as salt and basalt. Okay, so what's the motivation really? Is that full wave inversion, as it's being employed by the industry, is plagued by local minima. And that has been basically detrimental for the uptake of this technology because it requires a lot of hand-holding that we try to avoid. So what we'll do in this talk is derive an alternative extended formulation that uses a quite natural extension that allows you to fit the data for poor starting models and therefore will be less prone to local minima associated with cycle skips, which is computationally feasible. And it does all of this by relaxing the physics while still staying solidly grounded. Okay, so what are we trying to do with full wave inversion? We try to retrieve the median parameters from partial measurements of the solution of the wave equation, typically at the surface. And we use the wave equation to do this, where Qi is the source for the I-source experiment, Ui is the wave field, and Am parameterizes the wave equation, where M is, say, the velocity or the slowness. And we are interested in obtaining estimates for this velocity given data that we have acquired. So what most of the methods that we use to conduct this sort of wave inversion use is the so-called adjoint state or reduced space method. And there what we do is we optimize over Earth models to minimize the misfit between observed and simulated data while solving the wave equation exactly for each Earth model. On the other hand, you have so-called full-spaced or all-at-once methods that optimize over Earth models and wave fields jointly to minimize the misfit between observed and simulated data subject to wave fields that are consistent with the wave equation. So both of these aforementioned approaches assume flawless physics for each source. But they differ in the way they insist how this wave equation holds for each iteration. The adjoint state method basically insists that the wave equation holds exactly for each iteration, whereas these full space methods allow you for slack. In addition, these two approaches differ in the unknowns. The adjoint state only optimizes over the Earth models M, whereas the full space method optimizes both over the Earth models M and the wave fields U. So what we will do in our work is come up with a new approach that sort of holds the middle between these two approaches I just mentioned. And what we're going to do is we're going to take an ansatz where we assume for now that we know the wave field everywhere. And in that case, we can use the wave equation where we now know U for each source, Q, and we can then estimate M by solving a minimization problem that is listed at the second equation on the slide, which is very different from the equation that we use in adjoint state, where we invert the wave equation and then restrict to the receivers where you have the data, whereas in the other one we try to basically reconstruct the wave field everywhere through this pi-1, and then we can actually use the wave equation to update it for M, because the wave equation is linear in M if we know what U is. Now the challenge then, of course, is how can we reconstruct these wave fields from these partial measurements. Okay, and that's the essential idea of Wavefield reconstruction inversion. So suppose that we have some Earth model M and we fix it, then we reconstruct the wave fields by jointly fitting the observed data, the shot records, through the first equation and also the wave equation. So what we're actually doing is solving a least squares augmented wave equation where we try to find a wave field that both fits the data as well as the physics encoded in the matrix A that's parameterized by M. Now, if we know then these wave fields, we can fix a U, and then for each shot, we can try to get a model update by basically forcing the wave equation to hold to find an M that basically tries to minimize the difference between A on U and Q. Okay, so essentially the difference between the two methods, again summarized on this slide, is at the top what we would do in conventional adjoint state methods is use the wave equation times the wave field as the source, whereas in this approach we use the wave equation together with a sampling operator that work on the wave field, and that has to equal the source and the data. So we really force to fit the data. And that has a drastic effect, as we can see on this next slide, where on the left we have the observed data where there are reflected events. In the middle there's the initial data for a constant velocity starting model where there are no reflections. But if you do solve this data augmented wave equation that both tries to fit the physics as well as the data, we create these proxy reflection events, and those are the ones that are going to drive our inversions, and that's why our approach differs from other methods. Now, where does this all come from? The original formulation, that is sort of the mother of all formulations, is the PD constraint optimization formulation, where on the one hand we try to fit the data by finding wave fields that, restricted to the receivers, will give you the observed data, subject to that you are solving the wave equation. That's a fantastic formulation because it avoids having to solve the PDEs explicitly. It allows for sparse Gauss-Newton Hessians, and I will mention later why that's important, and it requires storing all the variables, both M and U, for all the sources, and that's where there's a problem because that's prohibitively large for industrial problems, and therefore this problem doesn't scale to industrial seismic problems. Okay. Now, the adjoint state formulation that everybody uses tries to avoid that, and it does that by eliminating the constraints. And that leads to this formulation in the equation on this slide, where we have to explicitly solve the wave equation for each source at each iteration. Now, the great thing about that, you don't need to store wave fields. It's a very suitable approach to do black box optimizations, for instance, through LDPGS, but it needs to solve both forward and adjoint wave equations. It's extremely nonlinear in the Earth model parameter M, which is a real complication. It leads to dense Hessians, which is not good. And it really, and that's the showstopper, it has very strong reliance on accurate starting models to avoid cycle skipping. So to avoid that, we are going to go with an alternative approximation, which is called WI, or a penalty formulation, where we replace the constraint by a two-norm penalty, which is the second term in this equation, preceded by this term lambda, that weighs the importance of the physics versus the data fit. Now, if that lambda goes to infinity, we get solutions that are the same as the adjoint state formulation, but we don't need to. The great thing about this formulation, we don't need to store all the wave fields. We don't need adjoint wave equation solves. We have sparse approximate Gauss-Newton Hessians, which are very beneficial, as we will show. It's less nonlinear in M, but one thing we have to do is you have to solve these data augmented wave equations, and but that can be done, and that is a topic outside the scope of this talk. Now, this work doesn't necessarily stand on itself. Some other work is done, for instance, the contrast source formulation, where the combined objective is similar, but the formulation is different such that it needs storage of all the wave fields for all sources, and that's really special about our approach, where we don't need to do that. And the reason we do not need to do that is because we use a variable projection method, where we first, for a given M, solve this augmented wave equation by solving this least squares problem on this slide, and then if we have these wave fields, we then construct a reduced objective and we optimize that for M. So that's the key idea, and it uses techniques from variable projection. So in the end, what we end up now is with a very simple algorithm where we can loop over the different sources, where on the left you see the WI method, where you see that you can have the gradient updates, which are now made out of a correlation between the solution of that data augmented wave equation that gives these proxy solutions and the PD residual. Those give the gradients, they accumulate over sources, and then we can use that as an update after a line search parameter alpha. Whereas on the right, we have the conventional method, where we have to solve both the forward and the adjoint wave equation, and where the gradients are given by the correlation of the wave field and the adjoint wave field, which are very different. In addition to this very different interpretation on how you compute your gradients, this approach also has the advantage that it has a diagonal or very sparse Hessian and that is easy to compute as compared to the conventional approach where you have dense, computationally infeasible Hessians. So let's look at an example now before we proceed to more serious examples at the end of this talk. And let's look what happens if we have a single model with a single reflector and we compute the forward and adjoint wave fields and this data augmented wave equation and the PDE residue. So on the left you see FWI where you have the forward wave field and the adjoint wave field, whereas on the right you have the reconstructed wave field and the PDE residue. So if I propagate these wave fields now, you can see that on the left there are no reflected waves in the forward wave field because that was a constant homogeneous medium, whereas on the right this data augmented equation introduces reflection events into the data, and that can be used for the gradient to compute the updates. And that's really key. So what happens is by having this objective of fitting both the data and the wave equation, it not only introduces reflection events in our Wavefield reconstructions that we can use in our inversions, but it also uses these events to update the velocity model by enforcing basically the wave equation. Now this method, as I mentioned, corresponds to a variable projection approach. It solves for U and N respectively. And it differs from the conventional reduced or adjoint formulations where you do not have these events and where the velocity is highly nonlinear in data, whereas that's much less the case for this method. Okay, so what does it do for us? So this is a slide that tries to explain for a very simple medium parameterized in terms of a gradient and an intercept, so two parameters, and we compute the misfit for this analytically. And you can see that for small lambda, that means we do not insist on the wave equation too much, that we do no longer have local minima. Whereas if the lambda increases, and in that limit we go basically to the standard adjoint state equation, you can see that local minima enters into the formulation, and that's exactly why we have trouble with the conventional formulation of full waveform inversion. Now here you see another example where we have a monochromatic wave field, and you can see that on the left the data is cycle skipped, whereas on the right, because we force both the data to be fit as well as the PDE, you can see that you're no longer cycle skipped, and you do that by introducing certain events in the data, and that will actually give information for the gradients to find the appropriate descent directions. Okay, so now let me go to some examples that shows the merit of this method, and I will show some examples where we know that FWI may fail. Okay, and these are velocity models where you have a low velocity kickback, so the velocity decreases, for instance, so rays are not necessarily coming back to the surface and make it very difficult for FWI to come up with something reasonable. And I will also look at high contrast, high velocity unconformities. And we will, in all cases, solve the Wavefield reconstruction inversion or carry it out for poor starting models. And we will do that by using multiple frequency sweeps, typically from low frequencies to high frequencies, and use that result as a warm start for our next inversion. I will also show you what the benefits are of additional convex total variation and asymmetric hinge loss constraints. And in the end, what we really will do is show how WI can be used to leverage reflected energy during the inversions. Okay, so I will start off with the BG compass model. And the challenge of this is it's a model that has a velocity kickback and very detailed geology. I listed a number of properties of the inversion which I will not state, but feel free to look them up on the slides. I will carry out the inversions over two frequency sweeps. Okay, so on the top we see the true velocity model, which is highly detailed and has geologically constrained complexity in it. And at the bottom we have the initial model. And we carry out the inversions from 5 Hz upwards using a frequency continuation method. And as you can see from the top, the results for FWI are stuck in the local minimum. The initial model was too poor, and the method is going off in completely the wrong direction. Whereas the result for Wavefield reconstruction inversion for lambda equals 1 is very reasonable compared to the original model, and manage to escape at the local minimum. And the reason for this is that if you look at the first gradient, for instance, you can see that the first update on the top of FWI is pointing in the wrong direction. The starting model is wrong, it's cycle skipped, and it's saying you're going, basically it's painting itself in a corner and will never be able to escape that. Whereas the first update for WI at the bottom is in the correct direction and is a good start for the inversion procedure to progress towards a good answer. This is a comparison here of the cross sections, and you can see that despite the fact that the initial model was quite poor, the WI is able to come up with very accurate inversion results at the different parts of the model. Now, why does this all work? Well, because this objective function actually is allowed to play around with the PDE misfit as well as the data misfit, and the data fit can sometimes increase at certain iterates. So sometimes you can maybe go for one in the wrong direction, but since you have more play, you can actually get your way out of these local minima. And that's basically related to the fact that WI has two variables it optimizes over, namely all the data and the Earth models, whereas the conventional method only optimizes over the Earth model itself, M. So in this bigger space, things become basically more convex, if you want, and therefore less prone to get stuck in the local minimum. And that's really the key idea. Okay, so now I go to a second example, which is based on the blind chevron benchmark. And the challenges here again are velocity kickbacks, very detailed geology, but otherwise than that we don't know anything, since this is a blind benchmark. And this is a starting model. It has a 8 kilometers offset. And it's one-dimensional, so it has very little information. And this is what WI gets us by first making sure that we fit the data. So what you can see here is the noisy line is the data set that was provided to us at a certain frequency, and lambda is the parameter we chose to fit this data at the 800 shot location and at 3 Hertz. And this is the inversion result. And I think what's really very encouraging about this is that it does include velocity lows. And we obtained this by working with the raw input data, and we didn't do anything, just run the inversion and get these results, which I think is very encouraging. And we also estimated the source, which you can see on the left. The amplitude is quite close to the source that was provided by chevron, and the phase is very accurately captured as well. Okay, now this brings me to the last benchmark, which is a very challenging benchmark in the sense that it has high contrast, high velocity unconformities, and we will start at high frequencies with a very poor initial model. Now I will run a movie for you where on the left we use conventional WI without any convex constraints, and on the right we will impose additional constraints that basically constrain the minimum maximum value, the total variation norm on the recovered slowness, and a directional hinge loss constraint. And I will show you details of that mathematically in a second. So the method here, I don't have time to go over too much, but we have a constraint optimization problem where we constrain both the TV norm as well as the hinge loss norm, which basically controls the steps that the inversion can take in the vertical direction. And we iterate on the following equation. But let me just go to the examples, and as I said, there are two movies. On the left, it's the conventional WI for this starting model, which basically gets stuck in the local minimum immediately, whereas on the right, these convex constraints make sure that the inversion keeps on making progress when it goes through the data 8 different times. 8 different times it will go over these different frequency sweeps, and you can see that it continues to update the model, and the final result is super encouraging because it not only delineates the top of the salt very accurately, but also the bottom of the salt. So it's really something that you could construe as a automatic salt flooding. Okay, so that brings me to my conclusion. I think we introduced a new method for wave equation-based inversion that basically benefits from the same extended search space as all-at-once methods, but with memory and CPU requirements of the adjoint state method. And we really invert both for the model as well as the wave fields, but in a computational feasible way. It's designed to fit the observed data and is also less nonlinear, and therefore it's less susceptible to local minima. Experiments show that the FWI succeeds where FWI is often known to fail because it uses reflected energy to invert low velocity kickbacks, and the convex constraints help it to really invert very complicated salt body WI problems. And you could therefore say that this is perhaps a candidate for automatic salt flooding. I would like to thank the co-workers of this work, Ernie Escher, Tristan van Leeuwen, Bas Peters, and Zilong Fang. I also have to unfortunately share with you that one of our co-workers, Ernie Escher, has never been able to see the end or the fruits of mostly his contributions, especially for this salt imaging. I would also like to thank the sponsors of my consortium for their support. Thank you.